Hello everyone, welcome to JCE Connect series of lectures. So in this particular lecture, I'll be starting module number 5, design of beams. So the syllabus contains introduction about the beams, then the beam types, lateral stability of beams, then the factors affecting lateral stability, behavior of beams in bending, design strength of laterally supported beams in bending, design of laterally unsupported beams. Only here you will be studying only the theoretical part, no numerical problems on this. Shear strength of steel beams, beam to beam connections, beam to column connections and column splices, and there is no numerical on beam to beam connections, beam to column connections and column splices. Only theoretical part you will be studying. So these are the contents of the syllabus provided. So let us start the introduction about the beams. So what are beams? As you know, the definition of beam. So that is when the length is considerably longer than the width and thickness, then the element is called as beam. So in applied mechanics, the bending is also called as a flexure, which characterizes the behavior of slender structural element subjected to an external load applied perpendicularly to the longitudinal axis of the element. So that element what we call as a beam. So beams are also called as flexural members, as I said. So since the bending is involved in a beams because of the load acting on the beam, the bending will be involving. So bending is nothing but a state of stress. So because of that, these elements are also called as flexural members, and they are generally found in members of bridges and in a roof trusses and the towers. Towers could be of any kind: TV tower, mobile tower, microwave towers. So in etc. you'll be getting the beams, and even steel buildings also the beams are you'll be getting the beams. So this is the figure which shows that generally the beams are been providing horizontally and supporting on both the sides, and the longitudinal axis is passing through the centroid of the beam, and the load is been acting vertically downward. So like this, the load will be acting like this on the beam, and which is subjecting to stress in the beam. Hence a beam is being subjecting to bending action. So the bending, as I said, it is nothing but a state of stress. Then the beams are structural members that support the loads which are applied transverse to their longitudinal axis. They are assumed to be placed horizontally and subjected to vertical loads. So this is about the beams. Then the load transfer by beam is primarily by bending and shear. So here the load is being transferred because of bending as well as shear. Then classification of beams. How the beams are being classified. So the flexural members have different names, such as the floor beams. Means these beams, depending upon their position and depending upon the structures where that element is being using, they are called by different names. Floor beams, a major beam of a floor system usually supporting joists in buildings, transverse beam in a bridge floor. and they are also called as stringers, members used in a bridges parallel to the traffic to carry the deck slab. They will be connected by a transverse floor beams. So let us look at this figure. Here you can see the floor beams and also the stringers. So floor beam is also called as a main beam, which is been providing, even it is called as a primary beams also. That is a major beam of a floor system, usually supporting joists. Joists are nothing but secondary beams. They are also called as secondary beams in buildings. Generally these floor beams will support the joists, and these are been providing transverse direction in bridges. So in bridges they are provided in a transverse directions. So here is marked floor beams and stringers. So stringers members are used in a bridges parallel to the traffic to carry the deck slab. They will be connected by transverse floor beams. So look at the beams here, stringer beams. They are provided here. They are marked here. The next, purlins. So beams are also called as purlins in some of the structures. So what are purlins? A roof beam usually supported by a roof trusses. They are called as a purlins. So another name for a beam and the structure where they are being using the name is purlin. And the beam is also called as a rafter. It acts as a rafter, that is a roof beam usually supporting purlins. So in this figure you can clearly see that purlins and rafters. So purlins are provided over the rafters, and the purlins will support the roof sheeting also. And beams are also called as a girders. These are most important beams which are frequently used at wide spacing in buildings and bridges. Mostly members carrying heavy loads. These are also called as a main or primary beams. And the joists, light members carrying a load from floor in buildings. These are also called as a secondary beams. And spandrels, exterior beams at the floor level of buildings which carry a part of the floor load and exterior wall. So let us look at this figure. You can clearly understand what we mean by the girder. So here the beam is being marked, and this beam is running between the columns, and that beam is called as this beam. I'll mark here. So this beam is called as a main beam, or it is also called as a girder. Generally it carries the heavy loads, and this girder support secondary beams. They are being called as a joists, and the joists in turn support the floor load, that is a slab, and the slab load is transferring to the joists. Joists are nothing but the secondary beams, and from the secondary beams the load is being transferring to the main beams, and these main beams are called as a girders. Generally or mostly the term girder is being used for the bridge structures, okay, or the member which carries the heavy loads is called as a girder. And one more name for the beam is a spandrel beam, generally provided at the exterior end of the building at floor level, is called as a spandrel beam. So exterior beams at the floor level of a building which carry a part of the floor load and exterior wall is called as a spandrel beam. Joists light members carrying a load from a floor in a buildings. These are also called as a secondary beams. Then the main beam girder. The next, lintels. So lintels are also acts as a beam, and these are members supporting a wall over a window or door openings. Generally these are been providing over a window or a door opening which supports the wall. Then the girds. So flexural members are also called as a girds, horizontal wall beams serving principally to resist bending due to wind, used to support a wall cladding in industrial buildings. So this generally providing in industrial buildings. So the different types of beams generally used in steel structures, that is the types of beams. An I shape is common cross section for a steel beam where the material in the flange at the top and bottom is most effective in resisting the bending moment, and the web provides for most of the shear resistance. Means suppose this is the I section you are using, and this I section, as I said, an I shape is common cross section for a steel beam where the material in the flange at the top and the bottom is most effective in resisting the bending moment. So the flanges are provided to resist the moment. These flanges both at the top as well as at the bottom, which will resist the bending moment, and the web will resist the shear. That is given here. I shape is common cross section for a steel beam where the material in the flanges at the top and bottom is most effective in resisting the bending moment, and the web provides for most of the shear resistance. Then the commonly used types are as follows. So the universal beams, that is the rolled sections, are being used as a beams. In this beam, material is concentrated in the flanges and are very efficient in resisting uniaxial bending. The commonly used sections as beams are I sections, channel sections, tube sections, rectangular, hollow sections shown in figure below, and simple I sections are used for a normal spans and loadings. All the geometrical properties available in IS 800 2007 for I section. So these are the sections which are being generally using in a steel structures as a beam element. That is a T-bar can be used as a beam element. Angle sections are also been using as a steel beam sections. Then the hollow sections are also been using as a beam element. Then the wide flange beam, generally this wide flange beam is called as a H beam. This also can be used as a beam element. Then I beam also used as a beam element, and the channel sections. So these are the some of the sections which are being using as a beam element. So this figure tells from more stiff to least stiff which section of the steel member provides more stiff, that is a more strength or the more strong element, that is given in a hierarchy, that is H section. Then next to H is the channel section, which is more stiffer, then the square section, then the angle section, then the T sections. So depending upon the situation, depending upon the load to be carried by the element, these sections are being used as a beam element. The next is a compound beams. So what are compound beams? It consists of a universal beam strengthened by a flange plates. This beam can resist bending in vertical as well as horizontal directions. So the compound beams are nothing but if the I section alone is not sufficient to carry the loads, then the flanges of the I sections are being uh, provided with cover plates both the sides, and hence it can able to carry the higher loads. So this is the figure tells about the compound beam, and even sometimes the I section is provided with a channel section, and if the load is very heavy and two I sections are being provided with the cover plate at on both the side of the flanges. And in the heavy structures like in bridge structures and all, if the span is very long, if the longer spans are to be providing, in that case the girders like this is called the plate girders, and the plate girders are to be used like this. And in this plate girders, vertical stiffness and as well as the horizontal stiffness, just to prevent from the buckling of web, these stiffeners are to be providing. This also called as a compound beam or built up sections. So the built up sections are used when the normal I section becomes inadequate due to large spans and loadings. These sections are also used due to other functional requirements. Then I section with cover plates are used when the loads are heavy and spans are large. If the depth of the beam is restricted due to functional reasons, smaller depth I sections with cover plates can be used. Additional cover plates increases the lateral load resistance with increase in IYY, that is moment of inertia about YY. Then the properties of ISMB and ISWB sections with cover plates are available in ISI handbook of, that is SP6. The two sections, that is two I sections with cover plates can be used when a very heavy loads and spans act on the beam. So the sometimes gantry girders, that gantry girders also acts as a beam element. They should be of heavier they should be a heavier strength. That is, gantry girders are used in industrial buildings to lift the loads. Even plate girders are used as a beam element where the span exceeds 20 meter and the loads are very heavy. Even box sections can also be used as a beam element. That is, box sections have a large torsional rigidity and can be used as a single cell, twin cell or multi-cell sections. The openings are advantageously used for service lines. And in all built-up beams, the fabrication cost is higher due to the provision of connections between the elements. The next comes composite beams. So this is also another type of a beam. So first type of we used universal beams, that is the rolled beams. Second is a composite beam, the built-up beam. Then third is a composite beam. It consists of a universal beam with a roof slab which gives continuous lateral support. The concrete floor over the beam provides the necessary lateral support to the compression flange to prevent the lateral buckling. About lateral buckling, in next part of this lecture I will be explaining about what exactly the lateral buckling. And generally, as you know, if you take a beam, if the load is been acting, generally the beam will bend like this. This is the deflection. This is the deflection. If it is taking place in plane bending, this is called as in plane bending, that is in plane flexure. If suppose the beam, this is the beam, if it is deflecting side way, that is lateral deflection. Okay, lateral deflection, then this is called as a lateral buckling. This is called as a lateral buckling. Then encased beams, rolled I-beams concealed in cement concrete. These beams derive added strength, economy and fire protection also. So this figure tells about the first case, that is composite beam. It consists of universal beam with roof slab which gives continuous lateral support. The concrete floor over the beam provides the necessary lateral support to the compression flange to prevent the lateral buckling. So here it is given beam in friction connection with the concrete, this one. So this kind of beams if you provide, means the compression flange is being restrained against lateral buckling. Otherwise, if you go on applying a load without providing any lateral support, then this beam may be subjecting to lateral deflection, or it is called a lateral buckling, that is it buckles sideway. So if you restrained its compression flange, hence it can be prevented from the lateral buckling. So this is the one way of preventing the lateral buckling, that is by providing concrete floor over the beam, which can be prevented the lateral buckling. Even sometimes a beam, that is I section, is connected with the shear studs into the concrete, that is lightweight steel decino. So again we can prevent the compression flange from the lateral buckling. And the encased beam is, this is the encased beam, that is a rolled I-beam concealed in a cement concrete. Completely it is encased in a cement concrete, that is a beam fully encased in a cement concrete, and these beams derive the added strength, economy and fire protection also. So these are the other types of beams, that is encased beams. Next, then castellated beams. So this is also one type of beams. So what are castellated beams? These beams are special sections fabricated from I sections and are used for light loads and large spans. The openings are advantageously used for a service lines. Let us look at this figure. So if an I section is provided with web like this openings produced by beams, original beam and this is a produced beam, this is a rectangular openings. If the webs are been providing in these shapes, you can look at the beam section. This is a sinusoidal opening. First one gives you sinusoidal opening. So this one is a sinusoidal opening. This is a circular opening. This is opening provided at the web. This is a hexagonal opening, rectangular opening, and this is also another types of openings. And this type of beams are called as a castellated beams. So look at this figure, you can clearly understand the castellated beam. What is a castellated beam? So at the web of the section, hole is been made, that is the opening is been made in a hexagonal shape. See the hexagonal shape. These kind of beams are called as castellated beams. These beams are special sections fabricated from I sections and are used for light loads and large spans. The openings are advantageously used for service lines. Then what are the optimum span range for different types of steel beams? So here are the types of beams and optimum span range and the applications. So angles. Angles are generally used as a beam element for 3 to 6 meter span, and these are generally used for lightly loaded beams such as roof purlins and sheeting rail. Second is a rolled I-beam, and these are generally used for a span range between 1 to 30 meter and used as a beams. Then castellated beam, as I shown previously, and generally used these castellated beams, that is a span range from 6 to 60 meter and long spans and light loads. The plate girders generally used for a span of 10 to 100 meter and long spans with a heavy loads as a bridge girders. Generally these plate girders are used in a bridge structures. Then the box girders, generally 15 meter to 200 meter span range, long spans, and they carry the heavy loads. And the trusses, 10 to 100 meter span range, long spans and moderate loads such as industrial roping. So these are the optimum span range for different types of steel beams. Then lateral stability of beams. So for a beam loaded predominantly by flexure, and the beams are being loaded in a transverse direction, that is exactly 90 degree to the longitudinal axis of the beam, and because of the loading, the beam is being subjecting to the bending stress. So the bending is nothing but a state of stress. Because of the loading, the in a beam the stresses are developed, and because of the stress the beam deflects, and that deflection what we call as a bending. And and for a beam, two essential requirements must be met to develop its full moment capacity. So the elements of a beam, that is flange and web, should not buckle locally. So this is the I section given. So you can see here a web is been marked and the flange is been marked. So if this element to be carried by a load predominantly, if this member is been subjecting to the loading, then it has to satisfy two essential conditions for its full moment capacity. What is that first condition? The elements of the beam. So elements of the beam means flange is one element and the web is another element. So the elements of a beam should not buckle locally. After loading, these elements of the beam should not buckle locally for its full moment capacity. If they buckle, then their stability get distorted. So look at this figure. Here you can clearly observe the buckling, that is local buckling in the top flange. So this type of buckling what we call as a locally buckle or local buckling of a top flange. So whenever the beam is been subjecting to loading, then it should not buckle in this way. That is, if you want to develop a full moment capacity, the beam element should not buckle like this. That is, here it has buckled, that is a flange element has buckled locally. So look at this another figure, you can clearly observe here. So it is a local buckling. If this is the I section, I'll show you this one. So this is the I section. When this I section is subjecting, and if you cut here and look the section, so this is that section AA. The flange can be seen like this, so it is locally buckled because of the flexure. And if you cut in this way and look at this section, that is section BB, this is the section BB, and which buckled locally, that is web of the I section has buckled, and this is the flange of the I section has buckled. This type of buckling what we call as a local buckling. Okay, this is the local buckling. So again I'm repeating, for lateral stability, if the beams are to be stable, that is the beam, two essential requirements must be met to develop its full moment capacity. The first criteria is the beam elements of the beam, that is a flange and web, should not buckle locally as shown in figure. So the local buckling phenomenon is shown in figure. So like this, the beam should not get buckle. The second criteria, the beam as a whole should not buckle laterally. So what do you mean by lateral buckling? So this is the sideway. So as the load is applying over the beam, if you apply a load like this, so if it is buckling sideway like this laterally, this is called lateral buckling. If at all the beam has to develop a full moment capacity, it should not buckle laterally. Okay. So this is another figure which tells about the lateral buckling. That is, the beam as a whole should not buckle laterally. To prevent failure from the local buckling, as I explained in previous slide, what is a local buckling? To prevent failure from the local buckling, the cross sections of the flange and the web chosen must be a plastic sections or compact section. So what do you mean by plastic section or a compact section? So these things I'll explain in next part of this lecture. What are a plastic section and what are compact sections? Then to prevent from lateral buckling, that is the second case. To prevent from lateral buckling, restraints are provided to the beam in the plane of the compression flange. Hence, such beams are called laterally restrained beams. So these are the restraints provided for the beams. So in this figure you can see a compression flange embedded in a slab. So if you provide like this, then you can prevent the beam from the lateral buckling. So this compression flange should not buckle laterally. If this flange is being embedded in a concrete slab, so it should not buckle laterally, which can be prevented from the lateral buckling. So if compression flange connected to the slab by shear connections, if the compression flange is connected to the slab by shear connections, so there also we can reduce the from the lateral, or we can prevent from the lateral buckling. Then another way of preventing the lateral buckling is, if a beams connected by a braces like this, if the bracings are using between the beams like this, hence a lateral buckling can be prevented. So these are the some means of preventing the lateral buckling. Then what are the factors affecting lateral stability? So elastic critical moment MCR as given in clause 8.2.2.1 of IS 800/2007 is applicable only to a beam of I section which is simply supported to the end moments. But in practical situations, the following factors vary from basic case and affect the lateral torsional buckling behaviors. The factors are beam cross section, support conditions, then the loading and its position. So these are the three factors which affects the lateral stability of the beam. That is a beam cross section, so it affects the lateral stability of the beam. Then the support condition also affects the lateral stability of the beam, and the loading type and its position, and means what type of load is been acting, where it is acting. So these all will affect the lateral stability of the beam. So let us take the first one, that is influence of cross section shape on the lateral torsional buckling. If the lateral buckling is involved with a torsion also, then it is called as a lateral torsional buckling. Structural sections are generally made up of either open or closed sections. That is, generally the beam sections are provided either by open sections or by closed sections. So what are open sections and closed sections? I sections, channel sections, angle sections, and the T sections are open sections, and tubular, round and rectangular box sections are closed sections. So when you compare it with that is a closed section, when you compare it with the open sections, closed sections such as the boxes and hollow shafts or tubes have a very high torsional stiffness, often as high as 100 times that of an open sections. The hollow circular tube is the most efficient shape for a torsional resistance, but is rarely employed as a beam element because of difficulties encountered in connecting to other members and lesser efficiency as flexural members. And I sections are commonly used due to their easy availability and ease of connections. I sections, channel sections, though they possess high major axis bending strength, they are relatively weak in their minor axis bending. Thus, it is convenient to connect such sections to adjacent members. Next is the support condition. How the support affects the lateral stability of the beam. The value of elastic critical moment MCR as in code IS 800/2007 is for an ideal case of simply supported beam. To obtain higher values of MCR, it is necessary to adopt other restraint conditions which results in better utilization of the section and thus saves the material. So the lateral buckling involves three kinds of deformations. They are lateral bending, twisting, and warping. So lateral bending means in plane flexure, then the twisting means out of plane flexure, that is when it buckles laterally, which involves the torsional effect also, that is called as a twisting, and the twisting is also accompanied by warping. The support should either completely prevent or offer no resistance to each type of deformations. The effect of various support conditions is taken into account by a way of parameters called effective length KL, given in table number 15 of IS 800/2007 for different end restraint. So the concept of effective length of compression flange incorporates the various types of support conditions. So when greater amount of lateral and torsional restraints is provided at the supports, the effective length is lesser than the actual length, and alternatively the length becomes more when there is a less restraints. Hence, if you want to prevent the beam from the lateral buckling, there should be a strong support conditions. That is it controls, that is the factor called KL, effective length factor, that is only given here when a greater amount of lateral and torsional resistance is provided at the supports, the effective length is less than the actual length, and alternatively the length becomes more when there is a less restraint. Then the effective length factor indirectly account for the increased laterals and torsional rigidities provided by the restraints. So this is the table given in IS 800-2007, that is for effective length for a simply supported beams. So conditions of restraints given here is a torsional restraint and a warping restraint, and loading condition is normal loading condition and also destabilizing loading. So destabilizing means the load keep on changing, that is a destabilizing load. And the torsional restraints prevents the rotational about the longitudinal axis. The warping restraints prevents the rotational about the flanges in its plane. Okay, so these are some of the conditions given for the effective length of the simply supported beam. Please go through this table number 15 of IS 800-2007 given about the restraints. The next last type is influence of type of loading. So the type of loading also affects the lateral stability of the beam. To take into account the non-uniform bending due to the wide range of loading pattern, a simple modified is applied to equation for MCR. So whatever the MCR equation is given in IS 800-2007 in clause number 8.2.2.1, so for that equation and modifier is been applied, a simple modifier for the loading pattern is been applied to take care of the lateral buckling, that is influence of type of loading. So the type of loading, at what intensity or what magnitude it is acting over the beam, and where it is acting, how it is acting. So these all affects the lateral stability of the beam. So to take care of this type of loading, a simple modifier is been applied, and which is given for the equation MCR, that is MCR equal to C1 MCR. So where MCR is the critical moment factor and C1 is the equivalent uniform moment. Thank you. Okay, so this is about introduction about beams, and in the next lecture, so I'll be discussing about the bending pattern of the beams and plastic methods.